go ahead and get into what I would argue is the other complication regarding tension members, and that's shear lag. We've talked about net area, I think, till we're all blue in the face, and I think it's time to get into to shear lag. If you understand net area and you understand shear lag, then tension member analysis and design will be pretty straightforward. So the idea behind accounting for shear lag really revolves around connections that are a lot like this. So we have a wide flange section, and you can see it's got bolted connections, and it's connected via the flanges. So we've got a series of bolts here. We've got a series of bolts here. So pop quiz. How many lines of bolts on each flange? 2. Remember, 2 lines of 5 bolts, just to ensure we're all remembering the terminology and everything. All right. So we've got this W section connected by flanges, but there's nothing going on in the web, right? No bolts in the web, okay? So ultimately what's going to happen is that's going to affect the way that the connection performs as it's being loaded. What's going to happen is something like this, and I argue that one of the easiest ways to describe it is to imagine you've got a really serene, nice, even creek flowing. You know, it's all symmetric. Everything's, the banks are at a 1-to-2 slope. Everything's nice and serene. You've got a nice, calm, stream of water flowing through it. And then you take a big boulder and set it right in the middle of the creek. Now, right there at that boulder, the water's going to be splashing and going all over the place. So the flow of the water right around that boulder is going to be quite disturbed, right? Now, down the way, down the creek a little bit, once the effect of that boulder has been somewhat negated, everything's going to go back to nice, cool, calm, even flow, right? Make sense? Well, the same thing is happening in a bolted connection. When we look at the gross section, gross section yielding, we're talking about out here where all the stresses are nice and uniform. What you're seeing here is an image of what's called a finite element analysis. This is looking at shear lag effects in tension members, and this contour, this sort of rainbow-looking image that you're seeing right here, is a visual representation of the stresses that are occurring right there around that connection. And you can see right around where the bolts are, the stresses are sort of hopping around all over the place. Like, we've got regions of very, very high stress, regions of very low stress, and it's just because the presence of a bolt introduces discontinuities in the stress field. It is what it is. Again, it goes back to the same thing of a boulder in a creek. The water's going to be splashing all over the place. The problem is, when we look at gross section yielding, we can ignore that because we're looking down here where the stresses are all nice and uniform. We're not talking about gross section yielding, though. Right here, we're talking about net section fracture. So when we, samurai sword or lightsaber the section, we're talking about right here. We have to be able to account for those irregularities in the stress field, okay? Now, the reason why we call it shear lag, if you're curious, and I think I mentioned this last time, but if you've got something like let's say you've got an angle, okay? So here's the angle, so the L shape, and let's say one side's bolted and the other isn't. Well, when I yank on that angle, that load's going to be transmitted through the bolts. So part of the angle's going to see that load, and part of it isn't. Because that part that isn't, as I'm yanking on it, that one part's kind of lagging behind. It's really not seeing that load. And since that internal stress phenomenon's a lot like a shear stress inside, we call that shear lag, okay? Does that make sense? Okay, now if you really want to start to, and I mean like analytically, hammer down towards the exact answer, this gets really tough in the world of mechanics. You either have to have some really complex computer modeling, or you've really got to, put your thinking cap on and get your, advanced mechanics and series solution, all that stuff out. You really got to do some really complex calculations to assess this, I would say, quote unquote, exactly. But we're not going to do that for every single bolted connection that's out there. We'd like to use some more approximate methods that represent the phenomenon as closely as possible.